My name is Sergey Kuksenko. I am from Oracle. I'm working in general on Java performance. But here, right now, I had to make a short talk about comparison of different GC performance. Of course, it will be very lightweight and very on top talk because of digging into a lot of details. We just have no time, and it will be not enough. So you probably saw that kind of slide. It's a large capital letters written here. Don't trust him. I love that. Okay, I'm working on Java performance for a very long time, and let's do. The key question: how many garbage collectors are in Java? Louder, please. How many? Okay, just in that version of Java. I'm working with Java 11. Okay, who care about legacy stuff? Okay, I'll show how to find it. Java has a very nice flag, print flags final. It prints all options which exist in Java. Everything, and also default values for that particular execution. I frequently use it to understand how it's configured. And I know that all GC options which turn on this, on that garbage collector, they start from word use and end with two letters GC. I did that grep, so I got 5 garbage collectors probably. It's not enough. What about experimental things? We should look future. We shouldn't stuck on something past. Okay, there is another option, unlock experimental VM options, which also show me this list of garbage collectors. So just a general survey of audience. Who is working on Java 11 here? Cool. 10. 9. Oh, a little bit better. 8. 7. Yeah, really? Nobody? Who? Thank you, guys. Okay, so here is a list of what I could think is a garbage collector right now in Java 11. Let's do a short overview of this stuff. First of all, concurrent maps sweep. Who is using that garbage collector right now? Yeah, I thought it was a little bit more useful right now. I have to disappoint you. It is deprecated since Java 9, and it will be removed. We could talk about that why, but after the presentation, if you wish. Okay, epsilon GC. Who heard something about epsilon GC? Okay, it's not a GC. It's not a garbage collector. There is some terminology misunderstanding here. Because of, we called some part of virtual machine garbage collector. But in reality, in order to collect garbage, you have to create garbage before. So in Java, garbage collector helps you not only create garbage, but also to create garbage. Because of all allocation before initially should pass through that system which called garbage collector. It's not a garbage collector, it's something more general, it's memory management. And epsilon GC is experimental things which help you to create garbage but can't help you to collect it. G1 GC is our everything, is our the most major GC with default since Java 9. Parallel, really it's the same thing, it's just a difference which still exists in options due to some legacy stuff. It's very old collector, but very nice. Serial, just a question, who is using serial GC right now? What for? Oh, memory footprint, okay, makes sense. Because of it's mostly like a, okay. And ZGC, who has heard about ZGC? It's our new promising feature, yes, I really like it. Also a little bit details about targeting of collectors like concurrent mark and sweep. It's low post targeting, epsilon GC just for experiment things and measuring something. G1 is nice default balance right now. Parallel provides high throughput. Serials, it's like, first of all, it's reference implementation, which hard to make wrong. And the second, it really gives you quite nice and small memory overhead. And ZGC, it's new, experimental, not yet fully completed, but it's definitely low pass and targeted large heaps GC. There is a plans to make ZGC in production in Java 12. I hope it will be done. Okay, a very short pick. Mostly I will talk about these three GC. Because of parallel, it's very nice old GC which we have. G1 is our default, and we did a lot of efforts about that. ZGC is something new which goes to have. I also will have CMS in some comparison charts just to show how concurrent mark and sweep works with other things, and probably nothing else. Serial is out of scope my presentation. This slide is showing how we distribute poses in our garbage collector. So parallel collector always do a pose either for young or for old collection. G1 has a pose for young collection, has a pose for old collection compaction, but didn't have a pose for mark, only initial small puzzles inside. And the ZGC, it's not a generational collector. There is no young collection in ZGC. It's just collection of the overall heap. And there is only small pauses in ZGC and all other things done in parallel. It's very interesting to understand how the performance of blue GC thread may have impact for green. Okay, let's continue. Which GC is better? Not from my point of view, from your point of view. Any suggestions? Or maybe we could make it some fight competition here? It depends. Yeah, it depends, definitely. Which GC is better for what? For throughput, for latency, for memory overhead. Also, I consider such things like ease of use or tuning. It's another stuff. I will start from the end of that slide because I have not a lot of things to tell about that, and just throughput latency, it's large things. I leave it to the end of the presentation. Just a short couple slides about memory. I've seen a lot of questions on Stack Overflow. Why? My Java takes larger memory than I tell you in the option -x, mx. Because of its nav. It's just a heap. We need something outside of heap. Even GC needs something outside of heap because of GC is a native code which works written on C, C++, whatever. It could be written on anything. And it definitely needs some allocation for itself. And sometimes it would be nice to know how many native memory is required, but this or that garbage collector, what's the difference? And happily Java, GTK, OpenGTK has a very nice feature which is called native memory tracking, which allows us to know all details. Native memory tracking will show not only GC memory, but it also shows you how many memory used by compiler, runtime, etc., etc. But only what we need is is GC. So what I did, I took one application. It's a greedy application. It eats memory very well, but unfortunately that application, maybe not unfortunately, that application strictly followed generational hypothesis, so it produced very lot young garbage, how a lot of applications do. And it's just an example. So, and I executed that application in 4 gigabytes of heap size, 8, 16, 32, 64. Sorry, 64 is my limit. I don't have 1 terabyte machines right now, but I would like to check it there. And here's absolute numbers for different garbage collectors. For these 4 CMS G1 parallel and the ZGC. And I see that the G1 and parallel is the most large consumer, and I was pretty impressed that ZGC takes less memory. It's memory outside of heap which used only by garbage collector, and is the same, but in percentage to the heap size. The same chart. Any questions here? Okay, we finish with native memory. It's not interesting for me. Sorry. Easy of use versus tuning. It's a different things. Easy of use, just you execute it and it works as you wish. Tuning, you have ability to put that button, to turn that things and make it as you want. So how to check it? I try to understand how we could configure different garbage collectors. And from my point of view, that option is that differentiation between easy of use and tuning. Then less options than easy of use. I shouldn't remember all that crap inside my memory. But then more options, then more freedom I have. Okay, so in general, GC have approximately more than 50 different options, which common for all GC. Maybe not a common for all, maybe some GC ignore them, but approximately 50, a little bit more. I don't know exactly how much. Okay, let's check. The most easy of use GC is parallel. I found 6 options. 6 options particularly for parallel GC. Okay, nice. The second one, ZGC, 8 options. Not a bit of much you can configure, but very easy to run. G1, 26 options. Sorry, that number is not exact. I did mistake because I extracted the number just looking into code. And people do mistakes every time. And our winner, concurrent microprocessor, 72 options for configuring CMS behavior. After that, I'm not surprised that there are a lot of third-party consultants which will tune your CMS garbage collector for a very large amount of money. I heard about that. Okay. Let's move further. Throughput and pauses. General thoughts about that thing. That GC is always cost, and also then less pause we have, then less throughput we have. Because of, as we saw in our pictures, if we move some GC activity from pauses into concurrent, it somehow interferes with us. Does it mean that GC always costs us throughput? What do you think? I just want to show you several demos. Probably I will have time for that. So this is Gmage Benchmark. How many guys here are familiar with Gmage? It's our benchmark, so believe me, it's nice, cool, perfectly well. So what we are doing in that benchmark, we have set of integers. The size of that set is 100,000 elements. And we just want to get a sum of all these integers inside that map. Very simple. I love Stream API, definitely. Okay. And let's just execute it. Sorry, I definitely can't beat anyone in ability to write code, but I can beat someone in ability to copy-paste code. But just execute. So this is execution of that benchmark in Epsilon GC, when no any actual GC does. And as you see in that code, we allocate nothing, just maybe internal stream structures. We just making a summation of our elements. And we got 144 operations per second. It's quite strange because of half an hour ago it was 150. Okay, let's consider is like some mistake. It's our Epsilon GC, it's theoretical without any GC overhead, it should be the best. Let's check how parallel GC works. I draft the same, set performance is the same. And let's check G1. The same, yeah? Do you remember that number? 145, 150 operations per second. Okay. Let's do the following. We execute parallel GC and we force GC GC collections between iterations. There are features inside Gmage which forces GC to work, to collect garbage. In the original, the first region benchmark, because of stream API takes a very, very small allocation, there were no actual allocation, no garbage collection cycles. And right now we get garbage collection cycle with parallel GC. No, yeah, it's only 5 times faster. Right now, remember that number, yeah? Right now, I'll execute that with G1, but I'm expecting until I'm putting in code from you to explain me what's the difference, why it works faster. No ideas? Excuse me? Exactly. So what parallel GC and G1 GC does when they collect garbage, they moved objects into other places, so-called relocation, copying. And they're intentionally doing attempts to collocate objects which are referenced together for improved memory performance. That implemented intentionally inside that GC, because of if we have object a reference to subsequent norms, there is a high probability that we'll track that access. And here's the number for G1. Not so huge boost as parallels. Here's different algorithms for collocation, but what we definitely got here from that example, that garbage collector collected garbage, relocated, shrink it together, it significantly improved cache performance. So for parallel GC, we got 2.5 times less cache misses and 5 times higher throughput. And for G1, numbers not so good, different algorithms used, but also very fine effect. Non-moving garbage collector like CMS can't provide such benefits. So it's just example that GC is not only some overhead of. GC may provide you performance benefits. Okay, let's continue about throughput and our poses, how garbage collector impact to performance. And I'll show another demo. This is number 3. What I have here? I have very short array of integers, not primitive because of its collector. I want to talk about references. Just 124 elements, and I'm shuffling elements inside that array, interchanging in random order. I'm doing shuffle. Very quite simple benchmark. Okay, let's check how it works. Again, we will start with epsilon GC, which will do nothing inside that loop. And because of we do shuffle, at random local random, which we use for shuffling, return for us primitive types, there is completely no allocation inside our benchmark. Completely no. GC won't work here. Not a millisecond, not a nanosecond of GC will be involved. Only just iterating of how everything works. What we get here? We get 360 operations per second for epsilon GC. Because there is no collection, we will use it as a reference, and we'll try to do the same with parallel GC. Yep. I'd say 1/3 of our performance gone. It's artificial benchmark. You can't believe that in your application it will be 1/3 of your performance gone, but just showing how it could be. And doing the same for G1. 3 times slower. Yeah? Not a good. Oh, of course we should check that this is the same with ZGC. Sorry guys, I constantly did a misprint when I trying to write unlock experimental VM options myself. So I'm copy pasting that for years. I have some file on my machine. 260, I'll just try to raise it up. Did you see? It's higher throughput than has G1 or even parallel load. So why we have penalty for our throughput? Short talk. The problem is in that benchmark when we do shuffling, we took one reference, one place of array and interchange it with another. So we write references. And garbage collector has such bad things which called write barriers for references. It's some actions which GC should perform to provide his proper activity when we operate with references. For parallel GC, it's quite a simple idea that GC have to save information of references which goes from old generation to young generation. For G1, there is two kind of write barriers. First of all, save the same information on reference from one region to another region, and the second kind of barrier is just when you rewriting some old value, we have to save information about old value if we are do concurrent marking. That barrier works not at all phases. And the most interesting thing that because of in that demos, I don't have a GC, and I don't have an issue between old generation and non-generation. All that penalties which you saw, it's just a small initial check of our write barriers. We don't go to slow pass, just initial check. Should we save something for GC use? Oh no, let's continue work. And only that small check caused such a huge difference. Why we have the best scores for ZGC, and definitely the best scores from all collectors, but also penalties for ZGC other. I just want to show another demo, but I have to say that ZGC doesn't have write barriers. ZGC do nothing on writing one reference to another. But for that I have another demo. We don't have a lot of information. It's the same array, but I'm even not trying to shuffle it. I just walking through 1,000 integers and make a sum of that elements. Yeah, okay. Let's check. Completely no location. Okay, let's check it with epsilon, no stuff, 180, 1,850 something, blah, blah. Okay, believe me, because I'm a little bit out of time, I won't show you for parallel load at G1, it's the same. But let's do that for ZGC. $1,200, quite a large difference. The problem is that ZGC has a so-called read barrier for ZGC. ZGC have to perform some actions when we just read the reference from heap. Like here, we are iterating our array, we are reading that reference, and it makes for us some penalties. And again, even in fast case. And the same for here. Our demonstration number 3, we don't only write. Of course, before write something, if we shuffle elements, we have to read it. We have read barrier, but it's significantly faster than write barriers for other garbage collectors. So, ZGC has no write barriers and has read barrier, and we read references from heap. If we are reading references from, for example, local variable inside our Java code, there is no read barrier because it's not from heap. Only reading references from heap. Okay, and another thing which may cost, who knows what reference comparison operations means? Short hint in it, write as double equal sign in Java. The problem here, x-axis is percentage of equal elements. Because of it may differ, we have 0, all not equals elements inside for that comparison, or just 1% of equals give different situation. That spike is particularly in all charts. It's how hardware branch prediction works. Just exists, but anyway, in all such situation, we could see that the average time for simple reference comparison for ZGC is higher than for all other garbage collector. The problem is that because of ZGC is using colored pointers, we have a pointer different some information directly stored inside pointer. It means that if we are comparing two references, we should avoid such details. We should say just is the same object or not, and it doesn't matter how marked it was by GC, and a little bit more action should be here. So indefinitely, any kind of GC could have impact of our Java code or our mutator, how it works. Like it could be write barriers, it could be read barriers, reference comparison, it could be something else. Different GC could have different things impacted here. And it's only inside Java code. But again, all concurrent GC have a threads which work in parallel with our Java code. And also that thread could evict our caches, could just steal CPU cycles from our activity. And everything that has some impact. And I'll just show you some numbers. Of course, it's just only example which I saw, but for comparison, it may be useful. Again, the very large application which took as much memory as you give to that application, but mostly in young generation. And checking the absolute performance on very large, on different set of heap sizes, from 4 gigabytes to 64 gigabytes. And is absolute throughput of that application. What we see? We see that parallel and G1 is quite relatively stable. Later on largest heaps, they became slower. I don't know why. I'll show you the next slide. CMS not work perfectly well. Works with very large heap, but I definitely impressed by ZGC. As I realized here, ZGC don't like small heaps, but on large heaps, throughput works perfectly well. It's because that in case of 4 gigabyte heap, it's not enough memory for ZGC to work. Almost all these 4 gigabytes is used. ZGC needs a free memory to work in any kind of concurrent low-pass collector loves to have a free memory to work. Another problem here is just realized with this drop with largest heaps is a compressed oops. Who know what compressed oops is? Okay, and who knows where they are working or not? By default. Of course, we could change that boundary by different options. By default, and one note, sorry, I forget, all examples on charts which I used here, I'm using default garbage collector configuration. I decided not to play with options, particularly for CMS, with these 72 options. I became crazy of that. I'm showing how it works. Maybe for CMS, for something else, tuning, it could be achieved much more higher, much more better throughput. I'm just showing it's like example. Here is a boundary for compressed oops. By default, on the left side, they turn on the right side, they turn off. I checked, I won't show a slide, I checked that if I turn off compressed oops completely, the scores for G1 and parallel, they're completely flat. It doesn't change of heap size for that particular application, but CMS is still falling down on large heap. It doesn't like hunting. Okay, it's a throughput. It's time to talk about pauses. It's a overall pause time through 3 minutes for that execution which we saw on the previous slide. And sorry, I can't fit it in the single slide without logarithmic scale. Be careful. Because of CMS, total time is killing everything. And ZGC total pause time is very, very, very nice for that execution. It's milliseconds and 3 minutes. 3 minutes, 180 seconds. And CMS took more than 10 seconds from that. Not very bad. It's a total time. Okay, it's distribution of pauses. It's the max pause time which I observed. ZGC is not visible on that chart, but it exists. The max long pause time for ZGC in that case was 2 milliseconds. This is 95 percentile of pause times. Distribution here, CMS looks like much better, and ZGC is still invisible. And differently, just some side distraction. I'm using for years. I'm using some Java IDE, and what I did definitely when I installed for myself next version, I'm going to script which executes that IDE. I cut off all CMS configuration parameters, and several years ago I setting up parallel GC. Right now I'm fine with G1 for myself, and I'm not have any issues with pauses inside my IDE when I'm writing code. I don't know why they do it. Okay. A little bit short discussion between GC pause and application latency. Who cares about garbage collector pause? Because we are writing an application and we are caring about application pause. We should think about how the period of time at which our JVM is not able to process client requests. Who cares about GC? But because of, in reality, GC pause, it's one large contributor into application pauses application latency, but it's not the single point of our latency. And really, you should read some. Probably read already some things about safe points, because in order to enter into GC pause, first of all, you have to achieve when all your working threads reach that safe points. We have a nice logging detail for that. We could look how it takes. And just an example which exists in Java 9 or before. And what I see here, I just quite a small, nice pause, 22 milliseconds, not large. But the application pause here, until my application reach all safe points, it's approximately 8 times faster. Exactly 7.5 times larger. So not only GC doing that. The problem is that, like in that particular example, inserting say 4 points inside tight loops is expensive. It was made some decision, let's don't insert safe points into short loops, let's consider all counted loops as short. It was done in hotspot and code generation for some period of time. Okay, thank you for guys from Red Hat who forced us to fix that issue. And right now, starting Java 10 and all newest, that problems with long counting loop, because here in application there is one thread with a very long counting loop, where there is no cutoff point. And until that loop is finished, we can't reach safe point, we have to wait. And if you are still using Java 8 or even Java 9, the only way for you is to turn off that option, which is turn off by default. It exists, but turn off by default. It will cost you significantly for performance of your loop, but it may be okay. Or there is also another option, don't play with options, you write your code that you shouldn't have counted loops inside your code or your libraries. It's also the way. And the same application, the same behavior, also G1, GC is here, after G10 or G11. This is approximately the same GC pause. It was 22 milliseconds there and 21 milliseconds here. And here is the total application pause. It's not the only things which could pause your GC. So if you have a very large pauses in your applications, it not always means that GC is the place who you should blame for that. Maybe it's a problems with loops. Maybe it's an issue that you have a lot of running threads. Maybe something else. Just for example, it's another. It's a nice example. It's a very nice short, small timings, but they could differ in your application. What also runtime virtual machine is doing inside of save point. Here, just this activity at the end of save point after GC pause, but it also takes time. All things takes times, and you have to check it if you wish to definitely reach low pause application. So that is why it was invented some industry standard benchmark, doesn't matter which, when nobody wants to measure GC pauses. We have an application and try to do something. We send a request to the application and we measure in time of that request. If GC in pause, we know that time of application is increased. It's what we want to achieve, not to take care about the pauses, just to care about application latency. And again, the same example, don't tune anything, execute it with default on 32 gigabytes heap size for different garbage collectors. What on this chart, what we measuring? The right group, no SLA, is the max available throughput of that application, which achieved. And we could see that in CMS, G1 and parallel pretty well, parallel even better than G1, and ZGC is losing. But all other charts, it's what is the maximum available throughput for my application when all requests in the 99th percentile reach certain particular latency which we required. So for example, for first group is 10 milliseconds. It means that what is maximum throughput of my application when 99% percentile of requests less than 10 milliseconds. If someone thinks 10 milliseconds is very strict restriction, you could look into 10 milliseconds. And here, just the numbers. And ZGCs definitely provide low pauses, but not provide you a high throughput if you don't care about any kind of pauses. Fine, I have 5 minutes and 2 slides for conclusion. We have time for questions. First of all, there is no universal GC. In general, there is a division, like if you need high throughput GC, use parallel. If you don't care about pauses, or you just want to pass a lot of bunch of data through night when you're sleeping, just use parallel GC. G1 with advanced tuning and etc. could provide you very low pauses, but not extra low. If you need something crazy, just try ZGC. And if you definitely need low pauses in your application and still you're working with CMS, anyway, try ZGC. Then more of you will try ZGC. Then more feedback we will provide for us. Then more bug issues we will create for us. Then faster ZGC will appear in production. Don't worry that it's not only experimental. Don't forget to upgrade new Java version. I'll show you. Java 10 is better than Java 9. And Java 9 is better than Java 8 from performance point of view. And the key question is here that all that numbers which I show you, all chart, is just an example. Your application could behave completely differently. I don't know why. And no one, only you could check it. I can do for you. I can say that that application is bad, etc. I definitely believe that, for example, it is possible to create some application and parallel GC will have much less poses than ZGC. Because I can prove that such application doesn't exist, but I just don't have such application. Maybe you have. You have to report for us. Let's do it. Questions, please. I have one interesting demo, which I didn't have time to show, about G1 and streaming versus collections, stream API versus collection. Do you want to look? Yeah, okay. Let's show. This is code. This is my first demo. When I get a sum of elements of set of integers, it's not just a set, it's tree set. Not hash set, it's tree set. It's intentionally. Here is an example when I'm doing it using stream API. Oh, sorry. And here is an example with number 2, where I'm doing the same thing. Also sum of elements of our tree set, but using standard classical iteration. What is better, stream API or iterators? Okay, let's check. So what we do? Let's start with parallel GC. I want forced GC for shrinking the data. No cheating, just clean execution. Okay, 147, and the same with iterator. Okay, 147. Cool. Let's do the same stuff with G1. It's warm up. Okay, 145. It's quite strange because of it should be the same as parallel. I mean about stream API, but let's deal with iterators. It's not a big difference. It's only 4 or 5% difference, but that code is 4 or 5% slower on G1 and only on G1 than that code. Any guess why? The question is the following. It's question of barriers. What happens inside iterator? When we are working in iterator, on each step we store the next element in our iterator. It's a set. And even it's not one element, we are passing through a tree, we are storing our place in our tree to get the next element. We perform store. So theoretically, it should be some effect of write barrier. Okay, why it's not visible in case of parallel GC? Because of iterator, it's a newly collected object, located inside Young. Our set is a very old object, it's an old generation. But parallel GC tracks only reference from old gen to Young, not from Young to gen. For G1, the situation is different. We have to track references from one region to another region. And because of this is young object iterator and this is old collection, here they're just in different regions. It doesn't matter is it young region or old region. Anyway, we have to track that reference. And here, G1 barrier, tracking that references for iterators, and it cost for us just 4%. But for Stream API, we don't have to store anything. Stream API, of course, create a lot of stuff, structures, functions, but in Stream API, we don't iterate each element. We shouldn't just store references inside heap for each step. It's just 4% differences, and for G1, Stream API is better than iterator, at least on that example. So that's all from me. Anything else? Thank you.